Okay, let's dive in. Look up at the stars and just wonder, is all this complexity built from just a few simple things, like a cosmic recipe with maybe only a handful of ingredients?
That's a great way to put it.
That's really what we're exploring today. We're doing a deep dive into the fundamental building blocks, the real basics of the universe, using this material, quarks, leptons, and the Big Bang, as our map, sort of.
And it taps right into this really deep human drive, doesn't it? This quest for simplicity.
Absolutely.
People have been asking forever, are there just a few basic objects, simple rules governing them, and maybe the biggest question, can we actually recreate how the universe started
Yeah.
right here?
Yeah, those are the huge questions driving particle physics.
Definitely, that desire to understand the origin. It's powerful.
And that idea of recreating the universe's birth, it still kind of blows my mind, but the source gets into how particle accelerators are basically, well, miniature Big Bangs.
Right, by smashing particles together at these incredibly high energies.
You're forcing matter back into those super hot, super dense states, like the first tiny fractions of a second.
Exactly. You're essentially creating conditions like the universe's infancy. It's like getting a little peek at how matter behaved right at the beginning.
So these lab experiments, they're not just abstract science. They actually tell cosmologists something crucial about the universe's story.
Oh, absolutely. How matter acts under that extreme pressure and heat gives us vital clues about the fundamental forces that shaped everything back then.
Okay, forces. The material lists the big four: strong, weak, electromagnetic, and gravity. Gravity, we feel. Electromagnetism, well, it runs our world. The strong force holds atoms together,
The nuclear glue, yeah.
but the weak force, that one always seems a bit more mysterious.
It is fascinating. The key thing about the weak force, you see, is its role as a transformer. It's unique because it can change the identity of a particle.
Change its identity.
Yeah, within the same generation, as they call it. So an electron can become an electron neutrino. A muon turns into a muon neutrino.
Wow, okay. So it's not just pushing or pulling, it's actually like changing one basic thing into another.
Precisely. And that ability is fundamental for things like how stars burn nuclear fusion and also for some types of radioactive decay. It affects both quarks and leptons, which is also unique.
So we have these particle families, and the weak force lets them kind of swap roles within the family. And the big picture that holds all this together,
Yeah.
that's the standard model, right? Our guide for particle reactions and how the universe evolved.
That's the framework, yes. A remarkably successful one, but it's not the whole story.
Right. That's where it gets tricky.
Exactly. The source points out that when you try to wind the clock back to the very instant of the Big Bang, our theories kind of, well, they break down
Too extreme.
way too extreme. The density, the temperature, it's beyond what our current math, especially combining gravity and quantum physics at that scale, can handle.
Like trying to use the physics of a puddle to describe a black hole singularity.
Something like that, yeah. The source mentions superstring theory as maybe a future path, but that's still very much, under development.
Still theoretical.
Very. And then if you look at the universe now, there are other huge puzzles, dark matter and dark energy.
Ah, yes. The big unknowns.
We see the effects of dark matter. Its gravity pulls on galaxies, holds them together. But we haven't actually detected the stuff itself.
Still invisible.
And dark energy,
Yeah.
this weird repulsive force speeding up the universe's expansion. It's like the cosmos has its foot on an anti-gravity gas pedal.
Yeah.
It's baffling.
It really puts things in perspective, doesn't it? How much we don't know, even with all the progress. Okay, let's shift gears a bit. Momentum. The source talks about how our understanding had to change for really fast stuff.
Right. So classical physics, Newton's laws, they work great for, baseballs and planets.
Everyday speeds.
Exactly. But experiments back in the early 1900s, like 1909 to 1915, showed that when things get close to the speed of light, Newton's momentum formula, mass times velocity, isn't quite right anymore. It needed a relativistic fix.
So Newton wasn't wrong, just incomplete for those extreme cases.
A very, very good approximation for most things.
Hmm.
But yeah, near light speed, you need that extra term the source gives. P equals mv divided by the square root of 1 minus v squared over c squared. Looks messy, but it works.
And momentum matters because
Yeah,
it's conserved, right?
that's the key. It's a conserved quantity. In any collision, any interaction, the total momentum before equals the total momentum after. Same for energy. These conservation laws are incredibly powerful tools for figuring out what happened in particle interactions.
And that leads to Einstein's big one, E squared equals P squared C squared plus M squared C fourth.
That's the one. It connects energy, momentum, and mass.
And it tells us something weird about massless particles, like photons, and maybe neutrinos, which are almost massless.
Right. If mass m is 0 or close to it, the equation simplifies. Energy basically equals momentum times c, EPC. And crucially, these particles have to travel at the speed of light. It's baked into their nature.
Wow, okay. Now, speaking of weird particle behavior, the double slit experiment, the source brings that up.
Ah, the classic. A cornerstone of quantum mechanics.
That's the one where electrons act like waves. You shoot them at two slits and you don't just get two lines on the screen behind them.
You get an interference pattern, ripples, like waves overlapping, even if you send the electrons through one at a time.
It looks like each one goes through both slits somehow, and it shows things are probabilistic. You can only say where it's likely to hit.
Precisely. It forces you to accept that quantum reality is fundamentally fuzzy, probabilistic, and totally unlike our everyday world. Wave-particle duality in action.
Mind-bending. Okay, back to leptons for a second. 3 generations, the source says. Electron, muon, tau, each with a neutrino partner.
Yep, 3 families, similar properties but different masses. Electron, muon, tau, and their respective neutrinos.
Like 3 tiers in the family tree. And the weak force, we said, acts within these generations. But the source hints at a puzzle with decays, like a muon decaying into an electron and some neutrinos.
Yes, that specific decay, O1EU plus Re plus E, is interesting. It highlights the need for conservation laws beyond just electric charge. We have something called lepton number.
Lepton number, like you have to keep track of electrons versus muons versus tellus.
Essentially, yes. There seems to be a separate conservation rule for each generation: electron number, muon number, tau number. These rules explain why certain decays happen and others don't, and why you get specific neutrinos in the mix. It adds another layer of quantum bookkeeping.
Got it. Subatomic accounting. Okay, what about quarks? The building blocks of protons and neutrons, right? Hadrons?
That's right. Quarks are the fundamental constituents of hadrons, and they have their own set of labels called flavors.
Flavors. Up, down, charm, strange, top, bottom. The names are kind of fun.
They are a bit whimsical, but these flavors are distinct internal properties, like quantum numbers, different from Lepton numbers. They determine how quarks interact. 6 types in total.
So each quark introduces itself. Hi, I'm up, or I'm strange, and these flavors matter for how particles decay.
Absolutely. Particle decay is just nature finding a way to spread energy out, moving from unstable, heavier particles to more stable, lighter ones.
Like a neutron decaying.
Exactly. Neutron to proton, electron, and an anti-electron neutrino. That's the weak force again. And then there's this property called strangeness.
Strangeness.
Yeah, another quantum number. The strong force conserves it. If you create particles via the strong force, the total strangeness doesn't change. But the weak force doesn't conserve it. That difference affects how strange particles are produced and how quickly they decay.
Okay, so the strong force is strict about strangeness. The weak force is more relaxed. Now, how did we even figure out quarks exist? You can't just, like, grab one, right?
No, you can't isolate a single quark. The evidence came from smashing things. Specifically, the deep inelastic scattering experiments at SLAC, the Stanford Linear Accelerator Center, in the late 60s.
Like Rutherford finding the nucleus, but smaller.
Kind of, yeah. They fired high-energy electrons at protons. The way the electrons scattered, bouncing off hard points inside the proton, showed there was internal structure. Richard Feynman called these point-like bits partons initially.
Partons, okay. So they inferred quarks by seeing what electrons bounced off inside the proton? Intense.
It was groundbreaking work, real subatomic exploration.
And doing that requires some serious hardware. Accelerators, like synchrotrons?
Oh yeah, synchrotrons use huge magnets to bend particles into a circle and radio waves in special cavities to kick them up to incredible energies near light speed.
And then you have colliders, like at CERN and Lee, and now the LHC.
Right. Colliders smash two beams together head-on for maximal energy impact. LEP uses electrons and positrons. LHC uses protons. There are also fixed-target experiments where one beam hits a stationary material. Different setups for different physics questions.
Okay, you smash them. Then you need to see the debris.
Yeah.
Detectors. The source mentions old cloud chambers, but now we have these huge, complex ones, like DDLPHI.
Modern detectors are unbelievable pieces of technology. Imagine layers upon layers of different sensors. Trackers follow the paths of charged particles bending in magnetic fields that gives momentum. Calorimeters absorb particles and measure their energy by the shower they create. Different subsystems identify electrons, muons, photons.
A giant 3D camera for particle shrapnel.
That's a good way to think about it, capturing those fleeting interactions.
Now, forces again. The modern view isn't just push and pull, it's about exchanging particles. Feynman diagrams.
Correct. We now understand forces as being mediated by exchange particles, virtual particles.
Yeah.
Electromagnetism uses photons. The diagrams are really useful shorthand.
Visual aids for the math.
Exactly. Lines for particles, vertices where they interact by swapping a force carrier. But they represent disturbances in underlying quantum fields. That's the deeper picture.
And this explains why some forces are short range, like the strong force.
Right. The strong force carriers, gluons, also carry the strong force charge called color themselves. This makes the force field kind of bundle up and not reach very far. For the weak force, it's short range because its carriers, the W and Z bosons, are very heavy.
Heavy? How did they get heavy?
That's where the Higgs field comes in. The W and Z bosons interact with the Higgs field, and that interaction gives them mass. The Higgs boson discovery at the LHC confirmed this mechanism.
The Higgs field, giving mass. Okay. And this is all part of quantum field theory, which sounds intense. Vacuum fluctuations, renormalization.
It's mathematically complex, yeah.
Sure.
Quantum field theory treats particles as excitations of fields filling space. Vacuum fluctuations are like the field jittering virtual particle pairs popping in and out of existence constantly due to quantum uncertainty.
Wow, empty space isn't really empty.
Not in quantum field theory. And renormalization. Well, that's a clever mathematical toolkit needed to handle infinities that pop up in calculations involving those virtual particles so we can get finite, sensible predictions that match experiments.
Taming infinities. Okay, so bringing it all together, how does all this micro stuff connect to the universe, to cosmology, the Big Bang?
Well, the Big Bang theory rests on solid observational pillars. The source mentions the big three. The universe is expanding Hubble's law.
Everything moving away from everything else.
Right. Second, the amount of hydrogen and helium we see matches what calculations predict was cooked in the first few minutes early universe nucleosynthesis.
Primordial element ratio.
And third, the cosmic microwave background, the CMB. That faint heat signature left over from when the universe was hot and dense, about 380,000 years after the start.
The afterglow. Solid evidence.
Very solid. And those first few minutes when helium formed, that was governed by the particle physics and forces we've been talking about, just at incredible temperatures.
It all connects, and understanding the whole universe's structure needs Einstein's general relativity, gravity as curved spacetime.
Yes. On the largest scales, gravity dominates, and Einstein's theory describes it as geometry. Mass and energy warp space-time, and that warping tells matter how to move.
The cosmic trampoline analogy. And the shape of that space-time could be flat, or curved like a sphere or a saddle? Euclidean Riemannian geometry?
Those are the possibilities, yeah.
Ugh.
Current evidence suggests the universe is very close to flat, geometrically speaking.
Okay, and forming galaxies. That's where dark matter comes back in.
Crucially, ordinary matter couldn't clump together fast enough on its own in the early universe because radiation pressure pushed it around. Dark matter, being immune to that pressure, started clumping much earlier due to gravity.
It made the gravitational potholes.
Kind of. It formed the invisible scaffolding. After the universe cooled enough for atoms to form recombination, ordinary matter could fall into those dark matter clumps, eventually forming stars and galaxies.
So dark matter was essential architect. What about inflation, the super fast expansion right at the start?
Inflation is a really powerful idea. It suggests the universe went through this exponential growth spurt in the first tiny fraction of a second.
Why propose that?
It solves some big puzzles. Like, why is the CMB temperature so incredibly uniform across the whole sky, even parts that shouldn't have had time to talk to each other? That's the horizon problem. Inflation stretches a tiny uniform patch to enormous size.
Okay, smooths things out.
It also explains why the universe seems so geometrically flat. Inflation stretches any initial curvature flat, like blowing up a balloon. And maybe most importantly, tiny quantum fluctuations during inflation could have been stretched into the seeds of cosmic structure, the density variations that grew into galaxies.
So it smooths the universe, but also plants the seeds for everything in it, maybe from Higgs field fluctuations.
That's one possibility being explored, yes.
Wild. And the source ends with something even wilder. Quantum cosmology, the universe from a quantum fluctuation.
Yeah, that's really out there on the edge of theoretical physics. The idea is maybe the nothing before the Big Bang wasn't truly nothing, but some kind of quantum state. And according to quantum rules, there's a tiny non-zero chance for a universe, a tiny bit of space-time, to just pop into existence from that state.
Tunneling into reality.
Sort of. And if that happened, inflation could potentially grab that tiny quantum bubble and blow it up into the cosmos we see. It's highly speculative, connecting quantum mechanics and general relativity at their most fundamental level.
Wow, okay. So, wrapping up this deep dive, it feels like the universe at its core is built from this, surprisingly short list of particles and forces.
It's sort of cosmic Lego set, yeah.
And particle physics labs are our way of playing with those Legos under extreme conditions, like peering back in time. But then you have dark matter, dark energy, huge reminders that the set isn't complete or we don't understand all the pieces.
Absolutely. There's still so much mystery. Our understanding is definitely still evolving.
Which leads to that final thought from the source. If the whole universe, everything we see, could have started as just a tiny quantum blip, maybe even one possibility among many, what does that really tell you about the nature of reality itself? It kind of makes you wonder, doesn't it? This dive into the very small really does open up some enormous questions.